Okay, so how do we compute this information gain, and how do we use it to make decisions in building the decision tree? All right. So let's go back to this simpler example of predicting when we're going to play golf or do some other outdoor activity. Okay. So before we've made any decision about the decision tree, we've got 14 records and 9 of which are labeled yes. They're positive examples. And so we can compute the unpredictability, the entropy of this data set, just as we have with the Titanic data set and with the die rolls and so on, and we get 0.94. Now, if we choose the outlook attribute to be the root of our tree or to be the next node in the tree, then we see that we'll have 4 records that are that represent overcast, right? If we choose the attribute outlook, then the value overcast has 4 records, all of which are yes. And so the entropy of that choice is going to be 0. Okay, it's 100% predictable, right? It's 0 unpredictability, all right? And the value rainy has 2 no's and 3 yeses. Okay, so 5 records total. 3 out of 5, log 2, 3 out of 5 plus 2 over 5, log 2, 2 over 5 is 0.97. Okay, and then finally, if it's sunny, then you have 3 no's and 2 yeses, and it's the same value, 0.97. Okay, and so now the expected new entropy, if we have chosen outlook, you compute expected value. Expected value is the probability of making that choice times the value of that choice. And so 4 out of 14 has a value of 0. 5 out of 14 has a value of 0.97, and 5 out of 14 has 0.97 again, right? And so compute the total there, and it's 0.69. Now, the gain here is the difference between where we started and where we end up. All right, so considering temperature, well, here we have 4 records. Sorry, for the value cool, we have 4 records. 1, 2, 3, 4. And we have yes, yes, no, and yes. And so 3 of them are yes out of 4. And you can compute the formula and you get 0.81. And you can do the same thing for rainy. Oh, excuse me. Should be hot, and this should be mild. All right, and so you can compute the same values here. And so with this one, so with hot, we have exactly 2 records are yes out of 4, and so that's 50-50. And remember, that's always unpredictability of 1. Okay. And then finally, when it's mild, there's 6 records, 4 yes, and we get an unpredictability of 0.92. And so then you plug in the formula, and the expected new entropy is 0.91. Okay. And so the gain here is less than it was for outlook. And next we can consider humidity, and here there's only 2 values. 7 records have normal humidity, and 6 of those are yes, and so the entropy is 0.59 if you plug in the numbers. And if humidity is high, so there's 7 records there as well, and only 2 of them are yes, and the entropy here is 0.86. And so the expected new entropy here is 0.725. And finally, windy, there's also only 2 values here. So if it is windy, there's 8 records with windy, 6 of which indicate we played, and the entropy is 0.81. And when it's not windy, there are 5 records, 3 of which we played, and the value is 0.97. And run through the numbers, and you get 0.87. Okay, so now we have a computation for every possible choice of attribute, and we compute these 4 gains. And it's really just the minimum of them, since we're subtracting the same value every time. And so outlook, the first one we did, is indeed the one with the highest gain, and so that's the one we'll pick. And so this sort of makes sense if you think about it. There's we went through the calculations here just to sort of try to help you internalize what's going on with entropy, but it does sort of make sense. It's the one that if you can choose an attribute that tells you exactly what's going on, you want to pick that one, right? So if you always play when it's sunny, right, that attribute tells you a lot of information by selecting that. So you want that one at the top. You want the most discriminative choices at the top. Okay. And just like we showed with that document classification example, we put, well, if the document includes the word Sunday, then we go over here and then we check and see if there's a sports team reference in it and determine the sports. And over here we'll choose if something related to science is in it. So really it wasn't much use to pick Sunday at the top. And in fact, I guess I have that on the next slide here. So which of these two has the higher information gain, right? If you include the word Falcons, well, Falcons might appear in some science articles and they also appear in some sports articles. And so let's say that down the tree about half are sports and about half are science on both branches. Okay. But if it includes the word Mars, it's not too likely to be about sports, and so only about 2% of the articles that include the word Mars will be about sports, while 95% will be about science. Let's make sure that adds up to 100. Okay. Fine. So which one of these has the higher information gain? Well, it includes Mars, and so that one would be chosen first. All right. Fine. So what's the algorithm here? Okay, so to summarize this algorithm, which is called the ID3 algorithm, assume all attributes are discrete, and we can discretize continuous attributes by binning them in particular intervals. And I'll give you a method to do that in a few slides. And then you're going to choose the attribute with the highest information gain and create branches, one for each value of the attribute. And then partition the examples based on the selected attributes so far, and you repeat with the remaining attributes on the remaining set of examples. Okay, and so you sort of recursively apply this. And then the stopping conditions are, well, when there's no more examples left, or all the examples along a branch are assigned the same label, because there's no more decisions to make at that point. Okay, and so this in this way you can apply this algorithm and build up a decision tree on your data set. And as you can see, this isn't too hard to implement. The maybe trickiest thing, if you're not familiar with it, is this notion of information gain, which we went through. But other than that, I hope you can imagine trying to write a program that would do this. There's a little bit of bookkeeping to do about building up this data structure, but it's not too complicated. All right. Okay, so what are some problems with this decision tree algorithm? Well, one is that it's expensive to train. You have to sort of keep inspecting these big chunks of the data set when you make every decision. And it's also prone to overfitting, which we haven't drilled into, but this is, in general, what overfitting means is you do really, really well on your training data, but you do poorly on test data, which is to say that the model doesn't generalize. Okay. And so you can imagine that you get these decision trees that are very, very good at making very precise decisions about the training set, but you give it one new example that it hasn't seen before, and it puts it into some bucket that may or may not be right. Okay. And so there's ways around this. You can try to prune branches of the tree that are over-specialized to particular conditions. Okay. And so remove or aggregate subtrees that don't provide much discriminatory power. But there's another way that we're going to talk about in the next segment that's very, very powerful. Okay. Okay, so before we do that, let's talk about how to split continuous attributes to make a decision with a reasonable number of branches, right? So one thing is you could split on every unique value, but given that a measurement value is a floating point number, it's unlikely for there to be too much grouping, in which case you'll have an individual branch for every possible value in the data set, every possible record in the data set, which gives you no information gain, or sorry, gives you a lot of information gain, but doesn't actually help that much. It sort of instantly overfits. Okay, so you want to sort of bucket these things. So how can you do this? So imagine with this weather data set, instead of having humidity labels of normal and high, we actually had the percent humidity as a number. Okay, and so one way to bucket this might be that, you know, we're going to say between 60 and 70 is one bucket, and between 70 and 80 is another bucket, and so on. But that requires some domain knowledge, and it ends up being sort of an extra decision you have to make when you're modeling this data. And we're trying to avoid decisions when we're applying these machine learning techniques. We don't want parameters in the system unless we have to. Okay, so what's a way to do this sort of algorithmically? Well, you can imagine that if we sort the data set in increasing order of humidity, pointing to the wrong screen, that every point in this humidity data set represents a possible place to split it into two choices, high and low. Okay, and so what we can do is just evaluate each one of those choices and measure the information gain and choose the point which gives us the highest information gain. Okay. And so here's what that might look like. I haven't actually checked every single one, but I sort of eyeballed it and saw that, wow, you know, the first several have solid yeses all the way up to here. So this might be a pretty good candidate to split on, because on one branch we know we're going to have nothing but yeses, and that's what we're looking for here. We're looking for reducing unpredictability, right? Information gain. Okay, and another good place to split perhaps is down here, because there's a lot of yeses, all but one above it, and no's above this, which sort of makes sense, because as the humidity goes up, we have we're less likely to play outside. Okay. So fine. So if you go ahead and compute the entropy here, here is 6 out of 6 are all yes, which means it's 0 entropy, totally predictable. And here it's 3 out of 8 plus 5 out of 8 entropy is 0.95. And here 9 out of 10 or 1 out of 10, that means it's a lower number as we'd expect, because it's pretty predictable, right? 90% chance of being a yes. And here 4 out of 4 is 0. Okay, and so now you do the expectation and say 8 out of 14 cases times 0.95 plus 6 out of 14 cases of 0 is a pretty low number, 0.54, but over here it's an even lower number, and so the right place to split is here. And I didn't check the others, but clearly these are the only places that will matter, because it didn't change in between there, which actually suggests an optimization. Okay, so again, we consider every possible binary partition and choose the partition with the highest gain as a way to turn any continuous variable into a discrete variable so that you can work on this. And you could actually do this more with, instead of just true false, or instead of just high low, you could also pick more buckets to have an even higher fan out.